Good day, all. Welcome to another episode of our video. This is an episode or whatever you want to call it. Hope all is good. Now, today we are going to be looking at Boolean expression, and Boolean expression is quite easy. But I want to be specific. I want to go into the laws in logic algebra. That's the laws in Boolean for Boolean expressions that we use in Boolean expressions. Boolean expression is more like your algebra, more like you having your variable and your constants. But in this in our Boolean expression, some things that we actually do in the ordinary algebra, we don't do it in this Boolean expression, and some things that we normally not do in ordinary algebra, we normally do it in this Boolean expression. So with that being said, let us move into the matter. Now, there are common rules in Boolean expression. One of them we have to be that of the zeros and one rules. In Boolean, we say if a Boolean algebra, this is our variable this time around. Now this a can either be 0 or 1, because we're talking in Boolean expression or in logic. In logic gates, we only talk about zeros and 1 and no other number. So this our a represents either 0 or 1, but not the two of them at the same time. It is either 0 or 1. Now, if you add it to 1, it will definitely give you what? 1. What I mean is this: 0, when a is 0, 0 plus 1 give us what? 1. When a is 1, 1 plus 1 give us what? 1. Remember, in your logic and gates, 1 plus 1 is 1. You normally say is what? 1. So that's the rule. And if we are multiplying by 1, if it was algebra, if this was a plus 1, we can't add this, but here we can. If this was normal algebra, we can't add this, but here we can. For Boolean expression, we can. So when you are adding 1 to whatever alphabet, this can be B, can be B bar, can be C bar, but so long 1 is adding any alphabet, everything turns to, it can even be 1 plus B plus C bar plus D plus E bar, go. So long 1 is here, the whole of this, it will definitely give you what? 1. So that's it for Boolean expression. So long 1 is, you're adding 1 to a variable or to an alphabet, it will definitely give you what? 1. Now, when you're multiplying 1 to an alphabet, it will give you that alphabet. Now, this one is common. This one, we actually use this one in our normal algebra or even normal multiplication, where we don't really say 1 times 1000 or whatever you want to say, or 1 times 200. This one will give us what? 200. So will give us what? 200. Now to prove it, this one will give us 100, not 200. Now to prove it, using this same ideology that we applied here, where we say that our A can either be 0 or 1. Now, if I apply this here, when A is 0, we're going to be having 0 times 1, which will give us what? 0. When A is 1, we have 1 times 1, which will give us what? 1. And if you see, this is 0, this is 1. This is the value of A. This is 0, this is 1. And this is the value of A. So, when 1 is multiplying any alphabet, it will definitely give you what? That alphabet. So it can be 1 times B times C times D. All of these things will still give you what? B, C, D. B, C, D. Another one is that of our 0. We have done for the ones. Let us do for the 0. Now when you are adding your alphabets to 0, it will definitely give you what? That alphabet. When you are adding an alphabet to 0, it will definitely give you what? The alphabet. Using that here, we have this plus 0 plus 0. 0 plus 0 will give us what? 0. And 0 plus 1 will give us what? 1. As you can see, it's still the same thing as your value of what? A. So here is for your A and here is for your 0. You're adding the two of them together. It's definitely giving you what? A. Another law is that of multiplication, and this one is also common. We know this one even in the multiplication table. We say when 0 is multiplying anything, we definitely get what? 0. So no matter who you are, as long as you're multiplied by 0, the answer is still what? 0. Okay. Now these ones are the easiest. These ones are the ones that we are to have in our fingertips. They are not even to be forgotten because they can be easily derived. It's not something that you should even cram. It's more like you cramming what 1 plus 1 is. Those things that can be easily proven. So it's not something you cram. Another law again that we will be going into will be what I call indempotency. Indempotency law. Now this rule, forget the much grammar. Also I'm talking about the variable adding itself, the variable multiplying itself. Now one unique thing in Boolean expression is that when we say A times A and when we say A plus A, normal algebra we say this is what? A square. And if it's a normal algebra, this one will give us what? 2A. But in Boolean expression is not so. There is no square, and the only number that we are only expected to be seeing is only 1. So 2 or square is not used. Instead, A times A will give you what? A. And A plus A will still give you what? A. So we can say when like terms are multiplying and adding, they will still give us what? The same thing. They will still give us what? The same thing. So you can have B bar times B bar. This will definitely give you what? B bar. You can also have C plus C. This will definitely give you what? C. So long they are alike, they will give you the same answer. To prove this, we have our a to be what? 0 and 1. Our a again, 0 and what? 1. When we are adding the two of them together, when we are multiplying the two of them together, we have that our answer to be what? 0 times 0, 0, 1 times 1, 1, which is still the value of what? A. When we are now adding the two of them together, we have 0 plus 0, which is still what? 0. And 1 plus 1. In algebra, in Boolean expression, we say is what? 1. In logic, we say is 1. So which is still what? The same thing. Which is still what? The same thing. So as you can see, a plus a is still a, and a times a is also what? A. So these are the easy ones. These are the easy ones. Another one again is the complement relation. Now this one is also easy. Now what we are looking at is that the relationship when we are multiplying a variable with its complement, and when we are adding it. So we can say something like a times a bar and a plus a bar. Now what will be our answer? So we are now having a multiplying what it is not. So if a is 1 and it is okay, no need of saying it, let's write it down. So let's say our a is 0 and 1, and our a bar will be what this guy is not, which is what? 1, and what this guy is not? 0. Now our a dot a bar, which will be the product of this is 0 times 1, we have 0. 1 times 0, we have what? 0. So the product of a variable and its complement is what? 0. But what of when they are adding each other? What will be our answer? If we were to find a plus a bar, this plus this 1, this plus this 1, which we can now say that a plus a bar will give us what? 1. So the sum of a variable and its a logic variable and its complement will give us what? 1. Now, so far we have been treating the easy ones. Now let us go a step forward. Let us go a step forward. I hope these ones have not been saved in your brain. These are supposed to be automatic. There's nothing hard about this, because this rule, one thing is to state it like this, another thing is to implement it, how to use it. Because the reason I'm going through this process of explaining these rules, or bringing out these rules, is because the main thing we're trying to achieve is how to reduce a Boolean expression if given to you. So these laws, you need to know them off heart, because at every single step you will have to go through all the rules and check which one can aid you in reducing a particular Boolean expression. So things like this are not that hard. These are not hard. These are the easiest. In fact, if there's anything that you should forget in Boolean expression, these ones are not among. These are the easiest. They are quite easy. If you understand the concepts like I have explained here, it's quite easy. You can even prove it even without, maybe if you have forgotten any of them, you can prove it simply using your one input and truth table. What this I just did here, 0 and 1, you can also use it and get your answer directly. So it is not something you cram. It is quite easy. And I would like to also say another trick I normally do use in my Boolean expression. I don't know if most students have adopted it. Whenever you are asked to reduce a particular, maybe you're given an assignment and you're asked to reduce a particular Boolean expression, when you are done with getting your answer, it's always good that you also plot, do the truth table of maybe if you're asked to reduce, do that of the one given and that of the reduced one. If we are giving you the same output, you are correct. We'll be talking about this more broadly in when we are solving one of these reduction rules. Now, moving over to our simple, the next simple ones. I like using the word simple because they are not actually hard. Actually hard. Now, we are going into now we just finished treating the rules. Now let us now start going into the laws. What we just treated now is the rules. Now let us start going into the laws. You might have heard of this. The first one will be our cumulative law. Now, this one is just about exchanging the position of your variables. In Boolean expression, you can exchange the position of your variables and to still give you a correct answer. It doesn't matter whether it's in front or at back. Each position can actually be interchanged. Now, one topic in maths that this doesn't apply is your matrix, and I think vectors too. This doesn't apply for matrix, because in matrix, when you have, especially when you're multiplying, it might apply for the addition, but for the multiplication own is not true for matrix. But in this place it works. You can easily interchange as you wish and as you want. Now another law again I'm going to be talking about is the distributive law. Easy. It's more like you opening your brackets. That's just what this is I'm all about. So in case if you have something like A in brackets B plus C, and you are asked to get its answer or product, it's going to give you A B plus A C. Just what opening your brackets. Now there is another law under distributive that is not in our normal algebra. Our normal algebra. This one is not in a normal algebra. This one is. This first one I've written now is in a normal algebra. But the next one I'm going to be writing now is not. Now, A plus B times C is equal to A times B. Sorry, A plus B times A plus C. Now, when I first learned of this, because I wasn't told in class, I had to research to find this. But when I discovered this, I had difficulty in understanding it, because I thought that you should be working both in algebra and in Boolean, like they should have small similarities. But this one is actually not true for algebra, but in Boolean is true. In Boolean expression, this works. So while you open your bracket here, your A multiplying this one and this can also work. This can also work. What this also means is that when you're given a equation, let me say A B plus B bar C. You can rewrite the whole of this to be A bar B plus B bar and A B plus C. This rule is mostly used in our POS. In our POS, that's a product of sum. When we want to find its mechanical form, this is the popular law that is used in it. So when you are, especially this distributive law normally used to look out for numbers that are single on their own. For this one, it's not compulsory it must be on its own. It can even be two. For instance, this one now. So what this means is that even the thing can also go the other way around. You can also have A plus B bar C and what? B plus B bar C. So this is correct. This is correct. So it is you that we know the one that you prefer, so you can get your answer quite easy and quickly. So know this. It will help you to come. It will help you. It will really help you, because I know say things choke my head now. To carry on all these things now, we feel hard person, but I guess when you practice with it, our advice after learning these laws or even working on the examples, you still go back and do some examples on your own. Try to reduce some Boolean expressions. It's actually fun. It's quite fun, very, very easy and fun. So when you see all those laws, it's not like you having your screwdriver and you're losing the knots. It's quite easy. So when you after this, I'll advise you to still get a question. Just try applying all this through. And you know one thing with Boolean expression, though they might tell you to reduce, even in that your reduced form, you can still create more other forms of your expression. It's fun if you take your time to just pick up any question in Boolean. I said, let me just play around with this. It's more like you having someone's telling you, giving you 2, and you start saying 1 plus 1. Then you then say 1. Okay, you can also say let's say 1 plus 1 factorial, something like that. 1 plus 0 factorial. Just whatever you know you can just do. Just play around with it. You can even say 1 plus 2 raised to power what 0. All these things are just you playing around with your answer. You can do 2 times 1. Like many things. Just how this Boolean expression is. It's quite fun. So when you know all those forms, using it won't be that hard. Okay, so the next law we're going to be going into is associative law. Now, this law is also easy, very, very easy. This one is just choosing the one to kind of factorize, or the one to, so it's more like you selecting a particular one to put in the bracket. So you can have a case where you are having something like A plus B plus C. You can decide, and this is in brackets, you can decide, so long the plus is here, there has to be a plus. There's a difference between this and this. They are not the same thing. This one, you notice that there's a plus in front of this. In this one, there isn't. So there's a multiplication sign there. I'm multiplying in this case. So they're not the same thing. So, but in this case, you can choose to write it like this, and you still be correct. or even in this form, and you will still be what? Correct. You still be what? Correct. Okay. Now another rule again we are going to be looking at is what you call the absorptive. Absorb. Correct. Absorption, to absorb. Absorption, I think is P. I know verse for engineer. Absorption what laws. Okay. Now, like the name says, we are absorbing. We are trying to swallow up some things. So I like the name cumulative, though I don't know the meaning of this word, but this distributive, yeah, we're trying to distributor. Associative, we are trying to association, understand? Now absorption also have its own principle. The reason for the name is that we are getting some things that we have seen, we have worked with, maybe proving through the truth table. We have seen that this is actually true. Now, one of it will be this: A plus AB is equal to what? A. So I'll be like, how is this so? How is this so? Okay, so in case let's say we want to use our distributive law, and we are assuming that it is in this form. We want to convert it back to this form. Now we'll be having something like this: A outside the brackets, we have 1 plus A B. Sorry, what am I saying? Now, like we said earlier, 1 plus any number or any alphabet will still give you what? 1. So the whole of this will still give us A multiplied by what? 1. Which is definitely going to give you what? A. So you see, I'm already doing small reduction rule here already. I'm already reducing some things here. But it's actually fun. It's actually fun. Another way you can also prove this, instead of you maybe if you are not good with all these laws, you can also use your truth table. Truth table is the always is the more affordable one for everyone. Everyone can easily use that one. That one is quite cheap. So that one doesn't require much technical thinking, only just carefulness. So with your truth table, you can tell yourself A and what B. Assign this is 2 inputs, so we're going to be having 4. So this is 0 0 1 1 0 1 0 1, and for our AB we have a multiple. So this is 0 0 0 1. 0 times 0 0 1 0 times 1 0 1 times 0 is 0, and 1 times 1 is what? 1. Now when you add this guy to this guy, let us see what we have. So when we add the two of them, we have that our answer will be what? Let's call it F. We have our answer to be what? So 0 plus 0 is what? 0. 0 plus 0 is what? 0. 1 plus 0 is what? 1. 1 plus 1 is what? 1. At the end of the day, you see it has the same pattern as that of what? A. So in case if you can't prove it using those reduction rule, your truth table will quite will be good. So, and please I'm begging you, know that this truth table I'm drawing, I'm not ruling my lines. So it's actually good that you rule your line, because most people we like to argue with you that that is not a table, so that line is there. So please try to add your own line when doing your truth table. Don't forget that. Now, another rule again we're going to be looking at, this is the first one. Another rule we're going to be looking at is A multiply by A B. Okay, A plus B. A multiply by A plus B. And they then ask you what will the answer be. Okay, now let me play around with this. If you are to open the bracket, you are going to be having A times A, which we say is A. When you're multiplying yourself, is still the same thing, A, and then plus A B. As you can see, we are getting the same thing as this. This and this are the same. So what it means that this will definitely give us what? A. Now I don't need to cram this. You could just simply just open bracket, anything. It's quite easy. It's quite easy, especially when you know the basics. Some other things just starts coming as easy stuffs. So let's do prove it with our truth table. We have our A and we have our B. 0, 0, 1, 1. Just to draw a line, indicate is a table. So we have a 0, 1, 0, 1. And A plus B will give us 0, 1, 1, 1. Then when we multiply it by our A, so we're going to be having this multiplied by this. We have the answer to be 0 times 0, 0. 0 times 1, 0. 1 times 1, 1. 1 times 1. So at the end of the day, you have this to be correct. So as you can see, this and this are actually what? The same thing. So we have succeeded in proving this. So what it truly means is that when we are multiplying our A to A plus B, it can be anything. It can be anything. But yes, it can be anything. So let us say in a case where we have 3 this thing. Are we still going to be having the same answer? Would that still be the case? So in a case where we are having A multiplied by A plus, so I don't know this. Let us try to prove if it will still give us what? A. Let's check to see if it still give us A. If we open this, we're going to be having A plus A B plus what? A C, right? Okay, now we know that this, from this law, we know that this is what? A. So we have A plus what? A C. Or better still, why am I even wasting my time like this? Let's make it more fun. You can also say like this. There are many ways to kill a rat in this Boolean expression. That's why I like it. You can be doing your own and you will still be correct. Another person will do his own to be different. Now we have multiplied this and this is what we got. Let us try to factorize again. We will now be having 1 plus B. Yeah, someone will be asking, but when they multiplied, it gave us this. Now when we factorize, it's not giving us this. That is Boolean expression for you. It is not like your algebra. It's not like your algebra. Yeah. So the reason for this is because A times A is what? A, and A times 1 is also A. So we're just manipulating and working with that. So, and like we said earlier, well, so long your 1 is adding any alphabet, it will definitely give you 1. So the whole of this two will still give you what? 1. So what this means is that so long A is in this bracket, so this can be A plus B plus C plus D plus again and be going. And so long the alphabet is outside and also inside that bracket and is unused O. This is true. So we are proving that it's only just for A plus B. It also work for A plus B plus C. It also work for A plus B plus C plus D. Now, another law again that we are going to be looking at is that of, okay, before we get to that, is the main boss, but we're coming to him. Another one we're going to be looking at is this: A plus A bar B. Now this one now has bar. That's just the difference between this and this guy. This one has what? Bar. You said the answer is what? Let's not write it first. Let's prove it. Okay. Now, looking at this, what can we say? If we are to use this rule, we can rewrite this as A plus A bar and A plus B. Now, A plus A bar will give us what? To give us 1. We have proven it before. So this will give us 1. But when it is times, if it was times here, this will give us what? 0. So this is what? 1. Now 1 multiply A plus B still remains what? A plus B. Meaning that this is going to give us what? A plus B. And this is actually true. Let's prove it with our truth table. With our truth table, we're going to be having A, B, and our A bar. Here is our 0, 0, 1, 1. Here is our 0, 1, 0, 1. So we'll be like, this thing you're writing 0, 0, 1, 1, 1, 0, 1, 0, 1. I have talked about this in one of my videos, or sir. Bringing it up again will actually be out of love. Okay. So the reason for this, like we said in one of the video, the law that we are using here is 2 raised to power what? N. 2 raised to power n. So your n is the number of input that you have. When we say input, we're talking about the number of how many alphabets we're having here. In this case, we're having 2, A and B. A and B are the 2 alphabets we're having here. So the number of alphabets is what you're going to be. So in this case, we're having 2 alphabets. A bar is not another alphabet. It's actually the negation of A. So it is dependent on what A is. So what we still have here is just what? 2 alphabets. So in that case, so what we're having is what? 2 raised to power 2, which will give us what? 4. So this 4 represents the number of possible combinations we're going to be having. The number of possible combinations that we are going to be having. So how we normally do it is the last one we have 0, 1, 0, 1. The next one 0, 0, 1. If there's another one in front of it, let's say another alphabet was in front of it, let's say C was in front, it's not going to be 4, 0, 4, 1. Another one 8, 0, 8, 1. In that order. So it's quite easy. If you still don't grab it, you can still refer back to my video. I made a clear explanation on that. Now, for us to negate our A, we'll be having what? 1, 1, 0, 0. Okay. Now our A bar multiplied by B will give us what? What will it give us? What will you give us? I'm asking you. Is you. Yeah. Okay. Yeah. So this times this will give us what? This times this will give us 0. This times this is 1. This times this 0. This times this 0. Okay. Now what will our final answer then be? So when we're adding this to A, which is A plus our A, this B. This is now going to be this add to this. So we're adding it 0 plus 0, 0, 0 plus 1, 1, 0, 0 plus 0. 1 plus 0 is 1. 1 plus 0 is 1. There is no like term here. Yes, because this plus this is equal to what? A plus B. Now let us do what? Let us check what A plus B will give us. Don't be offended that my line is dancing. No. Okay. Now for our A plus B, this is our A. We're adding it to B. So this is going to be 0 plus 0. This. Yama. So as you can see, the truth table is telling us it's actually what? True. So it is called the truth table for a reason. So in case if you're not sure about someone's truth, refer back to your what? Truth table. Okay. Now another confusion that normally do come with this law is because in some cases you will not it might have a different arrangement. You will have something like your A bar plus your A B. Now in this case now, what is now going to be your output? It's quite the same. If you notice, what we collected there is just the A that is on its own and the B. So in this case, it's now going to be our A bar plus what? B. You ask again, what if it is A plus A B bar? And B is not the one with the bar. It's not the same thing now. We're not talking about this one. This one will only work when the two A's are not the same, but so long they are the same here, we will still have the same answer as this, which is what? So despite what this guy is, so long we are having A here, and they're the same, this can be whatever. It's not compulsory, it must be B. We'll still end up at what? A. So you can still try all this I've said now with the truth table. So I will not be lying to you. So with that being said, we have dealt with the common ones. Now for the yoga pata, so we can go and rest. We don't try for this video. Please, if you have not subscribed to my channel, I'm begging you, please subscribe. Because your boy needs more motivation. I just didn't see 46 subscribers so far. I am begging you. I will still say, in case if it is you think there's a particular way I am following my own teaching that is leading to such results, please feel free to comment. Or why not me? Just leave that topic. Leave business out of studies. When you add the two of them together, they don't add up. They're not of oil and water. When you add the two of them up, one has to be the master, one has to be the slave. Okay. Now when we okay, the last boss, which is what? D. My lecturer will always call it D Morgan. He says an Igbo man. The man is an Igbo man. D Morgan. No, I think this one is French. I don't know. I think it's French. I think the first place I've heard of this name was in sets. He came up in sets. Those circles topic like that they did in foreign maths. But okay, so we're actually making use of his law here also. Now the Morgan rule are actually two. The first one says when you're having your A plus B plus C plus go you see, you add all these things are all inverted. That is, we call this what? NOR. The NOR of all these variables here will give us the product of the inverted what variables. We go to go. Understand? So this law, I just looked at it once. It just stuck in my head because it's quite easy. There's nothing there to cram. When you are seeing all bar and it's plus in the middle, when you're trying to separate the bar for each of them, then change to what? Multiplication. It's quite easy. I don't even see any need cramming this stuff. Now the second one is A dot B dot C dot D dot blah 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 blah, and you all bar it. All you have is A bar plus B bar plus C bar plus what? D bar. We go to go, you understand? End there, we go to go. So it can be more than just 4 to infinity. It works. So so long you're NANDing all these things. Yeah, I'm correct, it's NAND. So long you are the bar is for all of them, if you're trying to separate each of them on its own, the multiplication sign we have to change to what? Now someone will then ask me this question and say, what if you are having the two signs inside? What a very good question. I'll totally tell you that if you're having two signs inside there, you have to first of all group them into either SOP or POS. When I say SOP, I mean sum of product and product of sum. Okay, in case if that is confusing, let me try to solve with small example. The video is you're done with the video is over. You can pause now if you want, but I just want to try that question that just came up now. That's kind of a quick question. Now, what if we are having something like this? This is A plus B. Okay, A times B, and let's say times C plus D, and you're NANDing all of them. Will it still work? Will it still work? A very, very good question. Will it still work? Okay. The answer is yes, it will still work. We can take the product of all this to be a particular. Let's not go there. Because this will still give us A times B times C all bar times D bar. If you notice, the first one we worked on was what? That one with the plus. We separated it first of all, and we got this. Now from this other law can now work. You can now have A bar plus B bar plus C bar times what? D bar. So actually, even when they are combined, it actually works. What a finding. Okay, that's all for this video. That's all for this video. Please, this is this. We're doing end now. To teach the sweet to forget. To teach the sweet. Thank you all for watching my video. For watching this video, not my video. It is our video. Our good. See you in the next one. Goodbye.